So to continue with our previous discussion, so this time our focus is on external force convection. So we remember that when say external, so meaning the fluid here is unbounded. It is outside. When we say force convection, there is an intervention by a fan or a pump. So that is why we have external force convection. An important dimensionless number that we will frequently use in external force convection is our Reynolds number. So our Reynolds number is equal to the density rho times the velocity in meter per second. So we have x, this is the distance here along the length of a plate. Then we have our mu, our dynamic viscosity. In terms of kinematic viscosity, so our mu over rho is just equal to the kinematic viscosity v. So that's why we have velocity times the length over the viscosity. So that's why we have this Reynolds number. So the transition from laminar to turbulent occurs at the critical Reynolds number, which is 5 times 10 to the power of 5. So when the Reynolds number is less than 5 times 10 to the power of 5, then this is laminar flow. This is in this region here. But when our Reynolds number is greater than 5 times 10 to the power of 5, then we have a turbulent flow. So, in finding the value of the local friction and convection coefficients for parallel flow in a flat plate, so for laminar flow, so again, laminar, if Re is less than 5 times 10 to the power of 5. So if the Reynolds number is less than 5 times 10 to the power of 5, we will use these two equations. So we will use this equation in finding the friction coefficient and the Nusselt number using this value here. But remember that in using this equation, we need also to remember that the Prandtl number should also be greater than 0.6 in order for us to use this equation. If it is turbulent flow, so turbulent flow meaning the Reynolds number is greater than 5 times 10 to the power of 5 but less than 10 to the power of 7. So the flow is now turbulent, and the equations that we will use is this one and this one. So it depends on what type of flow, on which equation to use, whether it's laminar or turbulent. So first is we need to compute the value of the Reynolds number and also identify the value of the Prandtl number from the table. For the average friction coefficient in a flat plate, so this is what we are using more. So we have for laminar flow, we have the value of friction coefficient for turbulent flow, for combined flow, and for rough surface. It depends on the value of the Reynolds number. That's why Reynolds number is a very important quantity, because it will also dictate on which equation to use, whether it's laminar, turbulent, or combined. For the Nusselt number is helpful in finding the value of H. H is the convection heat transfer coefficient. We use H in finding the value of heat transfer from H delta T. So when the flow is laminar, so meaning the Reynolds number is less than 5 times 10 to the power of 5, we will use this equation to find the Nusselt number. For turbulent, so when the Prandtl number is between these values and the Reynolds number is between this value, so we will use this equation to find the Nusselt number. For isothermal surfaces with unheated starting point of length, the local last Nusselt number and the average friction coefficient will be So isothermal surfaces meaning, so the surfaces is not yet unheated. So the surface is at constant temperature. The surface is at constant temperature. So these are the equations that we can use for laminar turbulence. We can also use these equations in finding the value of the pH. And then we have here other equations. And these equations that you can see here, this is for the cross flow over cylinder and sphere. So this one is for cross, cylinder, and sphere. Kanina, that's for flat plate. So these equations are for cylinder and finding the value of the Nusselt number for cylinder and the Nusselt number for sphere. So this is a lengthy equation, but this is still very much useful. So let us have sample problem number 1. So during air cooling of potatoes, the heat transfer coefficient for combined convection, radiation, and evaporation is determined experimentally to be as. So this is the value based on the experiment. So we have the heat transfer coefficient, that is our H, and then the velocity, these are our V. So this is based on the experiment. Consider a 10 cm diameter potato. Initially, at 20 degrees Celsius, the thermal conductivity of potato is 0.49 watts per meter degree Celsius. In sum, that's 1 watt per meter Kelvin. Potatoes are cooled by refrigerated air at 5 degrees Celsius at a velocity of 1 meter per second. So we wanted to cool the potatoes through refrigerated air that is moving at a velocity of 1 meter per second at 5 degrees Celsius. So the questions are to determine the initial rate of heat transfer and then the initial value of the temperature gradient in the potato at the surface. So these assumptions are necessary, and it is you that will establish these assumptions in order to simplify the solution. So for this problem, we assume that this is a steady operating condition. Steady meaning that the conditions that being stated here are the properties doesn't change with time. Meaning the temperature of air will always be 5 degrees Celsius. The temperature of potato at that point will be 20 degrees Celsius. The potato, we need to assume that this is spherical so that we can use the equation that we have. So if it's not spherical, then we cannot use the equation. Though potatoes are not really spherical in shape, but mostly it's identical to sphere. So that's why it is being assumed here as well. Convection heat transfer coefficient is constant over the entire surface. This is also an important assumption so that we can evaluate in terms of the overall surface of the potato. So to compute the initial rate of heat transfer from Newton's law of cooling, so we know that from Newton's law of cooling, our convection is given by this formula. So Q convection is H delta S times surface area. So we need to compute the convection using these values. And if you're going to look at our given, we're given already with the value of, so if you're going to look at the given, so we're given with an initial velocity of 5 meter per second, 1 meter per second. And at 1 meter per second from the experiment, the value of heat transfer is 19.1 watt per meter squared Kelvin. That is why we use here H 19.1. That's why we have 19.1 because we evaluate it at an air velocity of 1 meter per second. the TS, so TS is the surface temperature of the potato that is given, that's 20 degrees Celsius. And then the fluid temperature, that is the temperature of the refrigerated air. So when we encounter this one, that is fluid, so that's 5 degrees Celsius. Our surface area, because our surface area here is a surface area of potato, which is a sphere. The surface area of sphere is pi d squared. That's why we have pi, diameter of the potato, which is 0.1 meter squared. That's why we have 9 watts here. So take note that some books will use surface area in terms of radius, but in terms of diameter, that's pi d squared. Another question is to find the value of the initial temperature gradient. So the temperature gradient is this one. So we discussed this one kanina. So diba, if you're familiar with this equation, the temperature gradient can be derived from this equation, then transforming this equation to this one. So from this equation, we have this one, which is already derived a while ago. So our delta t over delta y is just equals to s ds minus t infinity over k. So we also have the value for k. The value for k is already given. So we're going to look at the given. The thermal conductivity of the potato is 0.49 watts per meter degrees Celsius. So substituting all of this here in the equation, so our temperature gradient, or the temperature at any point along the radius, is the negative of this quantity here, and substituting all the values, we have negative 584.7 degrees Celsius per meter. So meaning, the temperature will vary per meter of the radius. So this is the difference of temperature per meter of the radius of the potato. Negative 584.7 degrees Celsius. So we will solve problem number 2 in the next video. So watch out for the next video.